Hello, my name is Soygür. I am a senior year EE student at Bilkent University. Today I'm going to present you my term project for E414 Introduction to CMOS VLSI Design course. Our task in this project was to design a 64-bit digital correlator. Throughout the project we went through the means methods of designing a digital integrated circuits, mostly using the utilities of Cadence software. As I mentioned, our task is to design a correlator, an IC made for identifying synchronization bit patterns at the beginning of a serial input data, even in the presence of noise. The device should take serial data as input, compare it with two 64-bit synchronization patterns, and if a match occurs, it should output a signal indicating the match. In order to detect the noise, an error margin should also be set. The device is given to be programmable with patterns and error margin of choice which are applied serially. This device also outputs which of patterns is matched and its polarity through two more output bits. Our project is divided into three parts, which are shown in this flowchart in detail. In part 1, I wrote a VHDL code in Vado software in order to describe the architecture and behavior of the correlator. I wrote in a single module and separated tasks with processes. The sync pin output is set high 2 clock cycles after receival of the sync pattern, so that I wrote the code accordingly. Below are the input pins and output pins of the correlator, which are declared in the entity part of the VHDL code. The internal signals, which can be considered as registers in the VHDL code, are declared in the architecture part, as well as the processes of saving data, saving the program, comparing, and synchronize, which adds the delay to the sync pin, so that it arrives always after 2 clock cycles. Followingly, I wrote a test bench code to simulate the behavioral of the correlator, and it passed the test with no errors. In part 2, after verifying my design with the test bench, I perform gate level synthesis with Janus software, which takes my behavioral VHDL code as input and outputs a gate level Verilog file. For the synthesis, I set the clock period to 80 nanoseconds to meet the timing requirements. And for designing the chip, I used the Innovus software. I firstly set the clock as 80 nanoseconds and supply voltage as 2.2 volts. Then I performed placement and routing, clock tree optimization, and at the end, timing and power analysis. The figures below show the pre and post clock tree optimization of my design. Since there's only one clock input pin, it is crucial to make this optimization so that the minimal delay is achieved and our system is not affected with delay related errors. And this is the final layout of my chip being displayed by the Virtuoso software after performing all the design steps in Innovus. At this step, the main design of my chip is complete, but in part 3, there's one more thing to be added. And this is the timing and power analysis table, which showed my results with different input voltages and with worst case and best case scenarios. In part 3, which is the final part, we are required to add a design for testability feature, and the chosen method is scan testing, which requires all flip-flops in design to be changed with scan flip-flops, shown in the figure. For this task, I regenerated the gate level Verilog file using Janus and generated the test pattern using Modus softwares. The procedures add 3 additional pins of scan enable, scan in and scan output pins to the design. After the simulation with test patterns, it yielded an adjusted test coverage of 97.77%, which means the scan can almost detect any error in faulty chips. Following this, I reperformed placement and routing and clock tree optimization using Innovus, and the diagram below shows the final pin placements. At the end, I performed more advanced timing verification and power estimation using Tempus and Voltus softwares, respectively. The table below shows the changes in their values prior and posterior DFT design. In overall, timing and power efficiencies slightly decreased, whereas total area of the chip slightly increased, which is a trade-off for being able to testing the chips. With final DFT steps being complete, the correlator IC is now ready to be sent to fabrication. An actual physical chip can be made by using the GDS file generated by Innovus software at the end. By using the test patterns we generated, every fabricated chip can be tested with high accuracies. Thank you for watching. I hope you enjoyed.